Let's look at a couple examples of converting complex numbers into polar form. So just a quick review here, a complex number in polar form is going to look like z equals r times the quantity cosine of theta plus I sine of theta. Okay, so r is the radial distance outward from the origin to our point on the complex plane, and theta is the rotation. So it's the same stuff that we saw when we had polar coordinates, but it's not an x and a y. It's not an r comma theta coordinate. It's going to have this r times cosine of theta plus I sine of theta. And that's, again, because we could rewrite this. If we distributed the r, you would have r cosine of theta plus I times r sine of theta, and that has the form a plus bi, right? And a plus bi is the complex format. It's the form of a complex number. So the a plus bi is rectangular form. The r times the cosine theta plus I sine theta is its polar form. So again, this is rectangular, and this is polar. Both of them are complex numbers, just they're different forms. So that means that when we do our conversions, a has to be r cosine of theta, which on our complex number plane, the x is the horizontal, sorry, the a is the real number, and that's the horizontal axis, which corresponds to x. B is the vertical axis, so that's going to be r sine theta, just like x and y. R squared is going to be a squared plus b squared, which really means r is just going to be the square root of a squared plus b squared. Technically, it should be plus or minus. Just to keep life simple, we're going to always go with the positive square root. And then we're also going to have to deal with tangent of theta is equal to b over a. If you replace a with x and b with y, it's the same equations that we saw when we were converting polar coordinates and polar equations. So it's the same equations, we're just using a's and b's instead of x's and y's. All right, so a couple examples here. Our first one, we have the complex number z equals 5 plus 5i. Just to kind of, so we know where that point is at. Again, the real axis is the horizontal axis. The imaginary axis is our vertical axis. And in this point, for this complex number 5 plus 5i, the a is 5 and the b is 5. So that means it goes 5 units to the right and 5 units up. And so 5 plus 5i is a complex number in the first quadrant. Okay, so we want to know what quadrant it is because that's going to help us determine the angle eventually. So to figure out what the complex number is in polar form, we want to figure out what r is going to be and what theta is. So for r, we can use r is equal to the square root of a squared plus b squared. So r will equal the square root of 5 squared plus 5 squared, which means r is going to be the square root of 25 plus 25. So r is equal to 50. And we can actually simplify that down. 50 is a 25 times 2, and so that 25 comes out as a 5, and then we're left with the square root of 2. So r is equal to 5 times the square root of 2. And again, we'll always go with the positive radius here. To find theta, we're going to use the tangent of theta is equal to b over a, right? That's y over x. So we know tangent of theta is equal to 5 over 5, which is a 1. So what angle makes tangent equal to a 1? And that angle has to be in the first quadrant, right? Because that's where our point was. Well, tangent's pi over 4. In the first quadrant, it's going to be pi over 4. So theta is going to be pi over 4. So if I wanted to write my complex number in polar form, I would have z is equal to 5 square root of 2 times the quantity cosine of pi over 4 plus I sine of pi over 4. So that would be my complex number. All right, let's try the second one here. So this time we have z is equal to the square root of 3 minus I. Okay, so this means that a is going to be the square root of 3, and b, well, so the b is whatever's in front of the I, which right now we don't actually see a number in front of I, but we would think of we can assume there's a 1 there. And the negative goes with that. So b is going to be a negative 1. All right, so we're going to follow the same process. R is the square root of a squared plus b squared. So R is equal to the square root of a square root of 3 squared plus a negative 1 squared, which means R is equal to the square root of 3 plus 1, which is a square root of 4. So R is going to equal 2. And then tangent of theta is going to be b over a. That means tangent of theta is going to be a negative 1 over a square root of 3. So what angle makes tangent a negative 1 over root 3? So again, we have a couple things to think about. Just in general, what angles make tangent be a 1 over square root of 3, whether positive or negative? And that would be a pi over 6 angle. So I know this has to relate to something with a pi over 6. And then we also have to think about what quadrant it is. So tangent is negative in the second and the fourth quadrant. Okay, so I need a pi over 6 angle in the second or the fourth quadrant. But we need to narrow that down to knowing specifically which angle we want. So let's go back to the original point. That's why I graphed the first one. So let's graph this one too. So again, real is the horizontal axis. Imaginary is the vertical axis. A is a square root of 3, so that means we're going to the right. The distance is square root of 3. And B is a negative 1, which means we're actually going to go down. So the complex number square root of 3 minus I is going to be in the fourth quadrant. So that tells me how I'm going to figure out what my theta angle would be. I know it has to be a pi over 6 to get a 1 over root 3. And I know it has to be the pi over 6 in the fourth quadrant. And so theta has to be 11 pi over 6. So that means my complex number is 2 times the cosine of 11 pi over 6 plus I times the sine of 11 pi over 6. Okay, so that's the complex number that's equivalent to the rectangular form of square root of 3 minus I. So we'll just leave both of those answers in complex form. If you wanted to check your answer to make sure that you did get it correct, go ahead and simplify those expressions. For example, number 2 here, we had 2 times the cosine of 11 pi over 6 plus I sine of 11 pi over 6. If we wanted to convert that back into rectangular form, we could just compute what the cosine and the sine values are. So what is the cosine of 11 pi over 6? Well, cosine of any pi over 6 is going to be a root 3 over 2. Since that's in the fourth quadrant, it's going to be a positive square root of 3 over 2 plus I times the sine of 11 pi over 6. Well, anytime you take the sine of something pi over 6, you're always going to get a half. And since 11 pi over 6 is in the fourth quadrant, we're actually going to get a negative 1/2 here. So we have 2 times the quantity, square root of 3 over 2, plus I times the negative half. And if you distribute that 2, the 2 is going to cancel with the root 3 over 2. It's going to cancel with the 2, so you're left with just the square root of 3. And then when you take 2 times the negative half, again, that reduces, and you're just left with a negative 1. So square root of 3 plus I times the negative 1 which you could rewrite as the square root of 3 minus I. So it does actually check, and that's also how we can convert from the polar form of a complex number into its rectangular form.